Everyone. This is Krishna. Here in this video, I am going to explain switching devices in power electronics subject. In the last video, when we have covered three different types of switching devices. Those are power diode, SCR, power BJT. So in this video, we are going to continue that previous class and taking one more switching device is called power MOSFET. Power MOSFET. So another device is power MOSFET. As we know, MOSFET, when we elaborate the MOSFET, that is metal oxide semiconductor field effect transistor. So what does it mean? Metal oxide semiconductor field effect transistor. So we are using this type of MOSFETs in power applications, means power level application. That's why we are using prefix as power. So we are calling this as a power MOSFET. So we are seeing basics of power MOSFETs, basics, then symbol of power MOSFET and structure of power MOSFET, then working of power MOSFET, how does it work, then we'll see VI characteristics of power MOSFET. Finally, we'll see the applications. So these are my outlines for this topic. The outlines are, I'm going to discuss about the basics of power MOSFET, and I'm taking symbol, how it is look like, and structure. Structure means the difference between normal MOSFET and power MOSFET. I'm going to discuss it. Then we will see the working of power MOSFET. Working, while doing the working, we are going to take the VI characteristics. How we are getting the VI characteristics also to be explained. Finally, we will see the applications. We'll go one by one. First, we'll see the basics. So, in the basics, we can say the first point is when we elaborate this MOSFET, it is metal oxide semiconductor field effect transistor. First point. Then second one is it can handle high currents and high powers when you compare with the normal MOSFETs. Then when we see this as high switching frequency, very important one, high switching frequency. The property of this power MOSFET is it has high switching frequency. High switching frequency. It is up to about 100 kilohertz. It is around 100 kilohertz. It's very important. Based on this property only, we are going to use this power MOSFET in many applications. And second one is it doesn't affected by the junction temperature. The junction temperature means what? The junction temperature mean basically it's not current dependent device. It is a voltage control device. When you compare this MOSFET with BJT, power BJT, what happened is where the power BJT is a current control device because the output current, collector current of the power MOSFET purely depends on the variation of the input current, that is collector base current, where the base current depends on the junction temperature. In case of power BJT, there is one disadvantage that because of this is that was a current control device depends on the variation of the base current that purely affected by the junction temperature. Now what happened in this case? Here it is a voltage control device. It is not current control device. That's why. So it does not affected by the junction temperatures. And next point is it is a voltage control device. Voltage control device. It is a voltage control device, and based on the first property, we are using this power MOSFET in many applications for the different switching frequencies. Basically, these are using for high frequency applications. We can say like analog electronics, where we are find the high frequency values in kilohertz, megahertz, like that. Okay, so these are some basic points that we have to remember about the power MOSFET. Next, we will see the symbol of power MOSFET. Symbol of power MOSFET. Symbol of power MOSFET. See this. This is drain. This is source, and this terminal is gate. This terminal is gate. This is the symbol of power MOSFET. As same as the normal MOSFET, there is no difference in the symbol. And you can see this is having three terminals. Three terminals: drain, source, gate. Okay. Coming to structure. Structure. We'll see structure of power MOSFET and normal MOSFET. We'll just compare both of them, how they are going to differ from each other. Okay. See, this is my P-type body. This is my P-type body. P-type body. Then see, this is my N-type material. This is N plus. I'm taking this is the structure. Okay. So this is source terminal. This is source terminal, and either sides. See this? This is the connection of gate terminal. This is connection of gate terminal. This is gate. Okay, and this portion is called silicon dioxide. Silicon dioxide material that we are using means we are connecting gate not directly to the body. Through there is one medium, that is silicon dioxide medium. The width of the silicon dioxide medium is around 1000 angstrom. Okay, and by placing this silicon dioxide material in between this, what happened is it possesses the capacitance property. It possesses the capacitance property, means it behaves like a capacitor. Then, as I said, this is a p-type body. This is n minus portion, then n plus. N minus portion and n plus. As we seen in the last class, in the last video, the size. When you see the centimeter cube, this will be 10 power 19 centimeter cube. 10 power 19 centimeter cube. This is around 10 power 14 centimeter cube. Then this is, now this is 10 power 16, and this is 10 power 14 centimeter cube. Again, this is 10 power 19 centimeter cube. So like this, there exist different doping values. So we can say this is my drain terminal. So this is the structure of power BJT. Look at this. This is P-type body, P-type material body. Upon that, what we are going to do? We are going to doping it N-type material like this. So source and drain both are highly doped material. Both the regions are highly doped ones. Whereas in the middle there is a lightly doped N portion is there. Lightly doped N portion here it is there. This is called drift layer. This is called drift layer. We know that what is the purpose of drift layer. Drift layer, if it is lightly doped, then what happened is it allows the current to flow immediately. If it is lightly doped, it is ready to allow the current values to flow inside the device. That's why we are using drifting, means it allows drifting property, thereby easily the current will flow inside the device, through the device. Okay, and as I said, one more point in this case, it has a large metal body. It has a large metal body, and due to that, the property of metal is it can easily bring out the heat from inside the body. So when you use the large metal for this device, automatically, as we said, there is a huge effect of heat for the semiconductor device, because these are what we say negative temperature coefficient devices. That's why more heat is going to be generated when we are using this one in operation. So that heat must be bring out from the device to the outside. For that, when you use the large metal as a body for that material, automatically the heat will come out. Means the metal will bring out the heat, means waste power in terms of heat. Okay, let us see the normal MOSFET. Let us see the normal MOSFET. I am taking NPN type, NPN. This is my drain. This is my source. Again, this is my gate. Here the gate is isolated. Gate is isolated, means insulated with some silicon dioxide material. This is silicon dioxide material. Here the silicon dioxide acting as a capacitance. Based on that property, the entire operation is depends on the capacitance property. Entire operation depends on the capacitance property. See this in case of MOSFETs, when we see the different types in MOSFET, the basic types of MOSFETs are depletion type MOSFETs and enhanced type MOSFETs. Depletion type MOSFETs and enhanced type MOSFETs. In that again, we can when we divide subdivide that two plus two things, we can get N channel enhanced MOSFET, P channel enhanced MOSFET. So again, N-channel depletion type MOSFETs and P-channel depletion type MOSFETs. These are the different types, four different types of MOSFETs are available in the market, but we are using enhanced type MOSFETs in this case, and the channel here is created by the N material. So N-channel MOSFETs, N-channel power MOSFETs, which we are using in our power applications. We are going to see that later on. And when you compare these two structures, look at this. When you compare these two structures, there is a huge difference in doping values. See, this is normally doped one. This is normally doped one because these are using for only signal level applications. When you go for the signal level applications, in the sense they are going to carry the microamperes to the milliampere of current, and they are going to handle the millivoltage of voltage values and going to handle only milliwattage of power. For that only, that there must not need that much of doping levels for this normal MOSFET. But when we are coming to this is using for high power application to carry the megawattage of power to handle the high currents. That's why doping levels must be very, very high. Particularly the outermost layers must be withstand with the higher values of the power. That's why maximum switching devices are made with high doping. The outermost layers are going to be making with high doping values. So like that we can remember this, we can analyze the structure of power MOSFET. Next we will see the working of power MOSFET. Next we will see the working of power MOSFET. These are the few things we can remember very easily. If it is normal P, if it is normal P, see centimeter cube in terms of 10 power 16, it is common to all type of materials. It is a normal doped one, then this is 10 power 16 values will be there. And if it is a lightly doped one, 10 power 14, just two number decreased, 16 to 14. If it is highly doped, three numbers increased. You can easily remember. See, this is 16, this is 16. Suppose it is a lightly doped one. If it is lightly doped one, decreasing 2 value. So 16 to 14. Okay. Suppose it is a highly doped one, then it is increasing to 3 times. It is increasing to 3 times. 10 power 19. Like that you can remember very easily the structure of the every switching devices. So next we will see the working of power MOSFET. Okay. So this you can use the entire board here. So take down again the structure of power MOSFET. This is my structure of power MOSFET. I am taking it in horizontal manner. This portion is N plus portion. This portion is N plus portion. This is N minus portion. As same as the previous one. This is P type body. As I said, this is the P type body. Okay, and we can say. So this is my. I am drawing here. This is my drain or source. You can take anything. This is my source I am taking here. And this is my drain. So two terminals. This is my source and this is my drain. Next, this is the silicon dioxide material. Silicon dioxide. This is my gate terminal. And as I said, it is a P type body. So body terminal. So what I am doing is I am going to connect this gate terminal to the body. Gate terminal to the body. See this. Like this. The battery, one battery we are going to connect to give the supply to that gate terminals like this. See, it is very careful to see the polarities of battery, connection of battery to the gate and body. Look at this. Plus positive of the battery is connected to the gate. Positive of the battery is connected to the gate. Negative of the battery is connected to the body. Negative of the battery is connected to the body. Then what happened is, if you are given supply through some body, let us call this one is VG. This I am calling VG. Then I am giving supply and entering into this one. As I said, this is silicon dioxide material possesses the capacitance property. Now, so outermost part of this silicon dioxide having the positive values, positive charge, you can say. Inner side we have the negative charge. This is the common capacitance property. So this side is plus, this side is plus, like this. Charge formed upon the silicon dioxide material. Inside this one, negatively charged. Negatively charged one. This means I am going to increasing the voltage value so that there is a negative charged particles are going to be increasing in p-type material like this. Like this, when you increase the gate voltage, automatically there is a formation of negative charged particle. You can say there is a electrons formation is there. You can say this is induced channel. Induced channel means we are creating one channel inside the P material to flow the current from source to drain. Like that, what happened? Here also majority carriers are electrons. 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 Means what? There is a path created inside the MOSFET with the help of capacitance property. Like that, what happened? Our current is going to be flows through the source to drain through the device and connecting one more supply to this drain and source like this. This is minus, this is plus. So this voltage I am calling VDS. This voltage I am calling what happened? If there is a path created to flow the current from source to drain, then automatically device comes to conduction state. Device comes to conduction state. And when you see the VI characteristics of power MOSFET, with the help of this working, you can able to draw the VI characteristics of power MOSFET. See this? There are two types of characteristics that we have to say. One is transfer characteristics, other one is output characteristics. Performance characteristics are two types. One is transfer characteristics, other one is output characteristics. Transfer characteristics are taking in between the input value and output value, and output characteristics are drawn between the VDS and ID. VDS and ID that generally we have called. Okay, we'll see characteristics. 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 First, we'll see the transfer characteristics. Transfer characteristics. characteristics are drawn between VG versus ID. Transfer characteristics are drawn between VG versus ID. This is VD, this is ID. VD, ID. X axis is VD, Y axis is ID. Okay, look at this. What is this? Nonlinear characteristics. As we know, semiconductors are possessing the nonlinear characteristics. Same way, even though some supply is applied across this one, to create a path, to form one path in the P material, needs some voltage drop, needs some time, needs some energy to be wasted. That's why, even though you are applying, sorry, this is VG. Even though we apply some gate voltage, it doesn't create the exact path to flow this current through source to drain. For that purpose, it is taking this much of voltage drop to create the path inside the P material. After that, it allows the current to flow. I current is going to be allowed through the device. So these are the transfer characteristics. When we see the output characteristics. Output characteristics. Output characteristics are drawn between VDS versus ID. VDS versus ID. This is VDS ID at constant VG. At constant VG values, we are taking the output characteristics. We can say performance characteristics of the power MOSFET also. See this. Look at this. So initially what happened is, even though gate current is option, gate voltage is option, we are applying some voltage VDS, we are applying some voltage, then what happened? Current is flowing like this, and after some breakdown voltage for every device. So far we discussed the every semiconductor device, every switching device having some breakdown voltage level. The same as this device is also having the breakdown voltage. After this breakdown voltage value automatically going to be breakdown. Here the breakdown circle like this. You can say this value is VC VDSO breakover voltage. So look at this VG. This is the VG1, VG2, VG3, VG4, and I am saying here is VG4 greater than VG3 is greater than VG2 is greater than VG1. Okay? So these are the output characteristics, and we can say these characteristics are consisting three main regions. Before applying gate signal to the gate terminal, this entire portion is called cutoff region. Entire region is called cutoff region. See this, there is a linear increment in current with respect to the voltage applied. That's why we can say this entire portion is called ohmic region. Ohmic region. This entire portion is called ohmic region. Then we see this is the portion where even though you are increasing the voltage across source and drain, there is no increment in the output value, output current, and you can say output current is constant. You can say this region is active region. So these are the main three regions that we can see in output characteristics of power MOSFET. These are the breakdown region. This is breakdown region. This is the breakdown region. Like this, you can able to see the characteristics of power MOSFET. And finally, coming to applications, because of its high switching frequency values, it is going to be used in many applications. Basically, these are going to be used in SFI system, UPS system. I'm writing here. I'm writing the applications of power MOSFET. Applications of power MOSFET. Applications of power MOSFET. Basically using any analog electronics, where the high switching frequency is needed. Based on the application values, if we are using analog electrons means, suppose the circuit need to operate at the frequency level kilohertz, then we go for the power MOSFET. We go for the power MOSFET. And second one is audio power amplifiers. Audio power amplifiers. Audio power amplifiers. Then third one, nowadays we are using to drill the walls and some metal. We are using power tools. In power tools also, we are going to use this type of material device for switching purpose. And coming to next one, next application is mining vehicles. In mining vehicles also we are using this type of power MOSFET. And next one is agricultural field. In agricultural field also we are using this type of device. As I said, SMPS, UPS system, and DC-DC converters as a switch. In DC-DC converter, when we see the configuration, so we are going to use the power MOSFET. IGBT also can be used, but based on its applications, we are going to use the power MOSFET. Meaning, we can say DC-DC converter. Then inverters also can use this type of device, inverters, etc. These are the few examples, few applications that we can see where we are using this type of power MOSFET. So that's why power MOSFET usage is more in power electronics. That's why you have to learn this one very carefully, and it is very useful for our life. It has to be remembered forever. Whenever the application comes, it must that we have to get the idea that here in this circuit we can able to use the power MOSFET based on that few features of power MOSFET. Okay, so in this class, in this video, in this we discussed the basics of power MOSFET, symbol we have seen, and structure of power MOSFET. Then its types, different types are there. I also explained that different types, and thereafter the structure we discussed, and got some idea about the difference between the basic structure, normal MOSFET structure and power MOSFET structure, and we have seen the different characteristics of power MOSFET. After that, finally we have got some knowledge about where we are using the power MOSFET in case of some applications. So in the next video, we will see the another type of switching device, that is power IGBT. So next continuation class is power IGBT. So far we discussed power diode, SCR, power BJT, and power MOSFET. This is the fourth switching device that we are using in power electronics. Two more devices are there, mainly using in power electronics. Those are power IGBT and GTO. So we are going to discuss that two types of devices in the next videos. Thank you.